Hey there. So I'm going to do a little recap from today's material for you guys and then start a couple of videos for you for tomorrow and the rest of the week so you can have it to rewatch before our exam. So yesterday was discovery of x-rays and the room, primary barriers, secondary barriers. Today was more about the EM spectrum. So I'm going to share my screen and just do a quick recap of that. We talked about what the atom was, the three main parts to the atom. The protons, the neutrons are in the nucleus. Protons are positive, neutrons are neutral. Around the nucleus, we have shells, starting with the K shell and working their way out, where you see the little negative electrons rotating around the atom. Each one of those electrons are held in, rotating around with binding energy, strongest binding energy being close to the nucleus. As you get away, it's less strength to those, what's holding them in place, you could say, was what that binding energy represents. We're going to talk a lot more about that in the upcoming chapters. Talk about different types of energy, forms of energy, where EM radiation is just one form of energy. On the EM spectrum, everything's in the form of a wave. So we talked a lot about wavelength and frequency in the waves and what that means. There's 7 different types of EM radiation. X-rays and gamma rays are just one part of that EM spectrum. And there's a special thing with X-rays that's a wave-particle duality of radiation, meaning that part of the time X-rays can be wavelength and frequency, just like on the EM spectrum. But once you get to a certain level, the higher the energy, you're going to get off that EM spectrum and come into what we call particulate radiation. And we're going to talk about those 2 types at the end. Had a couple of different pictures. I'm just going to get to the best one for the EM spectrum in the order of them. Know that everything on the EM spectrum has the same velocity, the speed of light. The things that are different: energy, wavelength, and frequency. So here's another little diagram starting at radio waves, going all the way to X-ray and gamma rays. But I like this one the best because it kind of tells you that relationship. Once we get to UV, that ends the ones who are non-ionizing. X-ray and gamma are considered ionizing. Their energy levels are so high that they can ionize atoms, specifically talking about our patient, our body, the atoms inside of us. If we have ionization happening, that's when damage can occur. Now, these relationships, we can talk about describing these wavelengths in different ways. If I'm talking about radio waves and microwaves, we're talking about a really big gap between the tops. That is a long wavelength, meaning it has lower energy and less frequency or low frequency. Down here, you can go to the gamma ray side. You can see how close together these little tops of the waves are. Short wavelength, meaning they have high energy or high frequency. Again, another thing, talking about the speed of light. They travel at the speed of light in a vacuum. So that's kind of an important thing to know about all of the EM spectrum, that they can travel at the speed of light. Here's our diagram that shows us how to measure the wavelength from the top of one to the top of the next. Frequency is another important thing. In a certain amount of time, how many of these peaks do we see? That is the frequency. Amplitude is the height of the wave. We don't really care about that so much. That's more if we're talking about sound waves. So that wave-particle duality was a kind of a concept thing where X-rays can interact with matter in an EM spectrum way when they're at a certain energy level, but they can also go off that spectrum and into particulate radiation. So they are duality word there, meaning they could be 2 things. Everything on the EM spectrum itself is a wave. So we call those waves a photon or a little packet of energy, a quantum, another name for it. We usually just say X-ray or photon. That energy is dependent on the wavelength. and the frequency. That's the energy. How much energy does it have? Shorter wavelengths have more energy. Radio waves, they're the lowest energy. Let's try to combine radio and low at the same time. Radio waves is very long wavelengths, you could say. We do use radio waves in MRI. They do not ionize. Microwaves is next on our spectrum. Then we got infrared, UV light, visible light. Well, I messed that up, didn't I? Visible light first, then UV light. Then our ionizing X-rays and gamma rays are at the end. These can cause skin burns. They can cause ionization to our body. Highest energy on the spectrum, where they originate from is the difference. X-rays from the electrons, gamma from the nucleus. Ionization is the big thing. That is when an atom is getting ionized, meaning it has the ability to knock out electrons, or adding or removing an electron from the orbit is ionization. Ionization is what makes us have to get a license, what makes X-rays dangerous, why you have to have a prescription for X-rays. They can damage the DNA molecules in our cells. Another little thing about the relationship of these wavelengths you need to know, they are inversely proportional, meaning they're opposite. Wavelength and frequency, opposites. Frequency and energy are direct, or they go together the same way. If we increase frequency, we're increasing energy. Increase frequency, increase energy. If we increase frequency, more frequent, that's a shorter wavelength or a decrease in wavelength. So opposites there. A couple of different ways to say it. If we're talking about X-ray beam or a photon in the beam, if we're saying a long wavelength, that's a lower energy, less penetrating. If we have a short wavelength, that's high frequency, high energy. Alpha and betas are our two particulates. Those are more in nuke med, radiation therapy. They are going to be a little different. They don't move at the speed of light. They're not on the EM spectrum. Radioactivity is something that is got to be understood for us, because we're going to be dealing with patients who may have had a nuclear medicine study and they are going to be radioactive. When things decay, these radioactive materials change and they become something else. That's called its half-life. That's the time it takes to decay for half of those atoms to decay down. Alpha particles, specifically what you need to know about these is they're very, very short range, can't go very far, don't move very fast, very large, can't penetrate very much, maybe a book. They originate from the center, the nucleus. It's from two protons and 2 neutrons. Beta particles also are coming from the nucleus, but it's an electron. It's a crazy thing that happens when beta particles are being made. They're lighter and smaller than the alphas. They can penetrate very thin things against, can't really penetrate much, but something like a piece of paper could absorb them. They also can ionize. That's why we have to go to school. We're the protector for our patients. We understand all of the things on the EM spectrum. Within that chapter, we also looked at the inverse square law. So I'm going to find my little link to that under Tuesday. Here's my link for the waves, inverse square law. So inverse square law is what we use when we're trying to see the relationship of the radiation from the source, from the tube, we could say, and how much radiation we're going to get at a different distance. Or we could say the IR, how much exposure is the IR going to get? How much exposure could we get? How much exposure would the IR be getting? So usually you'll see this in millisievert for the dose to us. Have 2 feet from the source, you get 40 millisieverts. What do you think will happen when you move to 4 feet or double the distance? Well, the inverse square laws states in the definition that if you increase your distance, the exposure the intensity is going to decrease by a factor of the square of the distance. So you can write that as the intensity 1 over intensity 2 is equal to distance 2 over distance 1 squared. You can flip those around as long as they're inverse. It's going to work out for the math formula. So we're going to put 2 over 4. We're going from 2 feet to 4 feet. Now, our dose is 40. So we're going to put 40 opposite of 2 in our formula, and we're going to put x opposite of the 4. So whichever way you want to write it. I know in my head that 2 over 4 is going to be a factor of 2. So 2 squared is 4. So it's going to be 4 times less if we double our distance. Now that only works in doubling or halving. It'll be 4 times less or 4 times more. So you really do need to know the formula to do the math. So if our dose was 40, I'm going to get 4 times less dose, so it's going to be 10, a lot less dose if I move back to 4 feet from 2 feet. The formula is going to be helpful, but always ask yourself, if you're getting closer or further away, am I going to be having a higher number or a lower number? That will let you know if you set the problem up from the get-go. There's kind of a drawing out of another problem. So on this one, we have 7 and we have x. We don't know what our dose x was. So 7 must have been at 3 feet. What's going to happen at 14 feet? So I'm going from 3 feet to 14 feet. It's going to be a lot less. Over here, we end up with 1.5. Now we have more formulas we're going to learn later. We got the direct square law, opposite of the inverse square law. This is a video from YouTube that I was telling you about. You can save this. He has a lot of samples of all of the formulas that you'll need to know for the program. We'll go into all these formulas as you get through the program. If you like math, you will be good. It's just a lot at one time, so we kind of break it up over the program. All right, that was it for today. So, trying to decide, should I stop? Yes, I'm going to stop. I'm going to share this video, and then I will start a new one.